Okay, so I don't know if anyone's ever done this like bubble stuff before, but it's so much fun. Okay, my buddy of mine and I did this one day, and I lost because he was like a university wrestler, so about this tall and 200 pounds, and built like a square. Right? So he had a very low center of gravity, and I came running at him as fast as I could, which is way faster than he could run, but it didn't matter, because he just got down low, and I ran into him, and then I bounced off, and flew backwards, and landed on my back, and it was like a turtle flipped over on its shell. There's not much you can do when you're lying on your back in the bubble, and you just kind of sit there and look panicked. And then he came over and jumped on top of me. Then he bounced off, because I had the advantage of all the mass of the ground underneath me. So, here's what we got to do. We got to understand one thing about this situation. Both people have one thing in common. Basically, everything else is going to be different, but there's one thing that's the same for both of them. What is it?
Acceleration.
Nope, the acceleration will be different.
The time?
Okay, sorry. There are two things. You're absolutely right. The time is also going to be the same, but what's the other thing that's going to be the same? Think about Newton's third law here. Force. Okay? Whatever force is on one of them, it's the same on the other, but in the opposite direction. Okay, and the time. Tell you, that's good snag. The time is also the same, because the collision lasts the same amount of time for both. Okay? All right, so what I want to do here then is actually isolate the two masses and see what I can calculate with the information for each mass, knowing that time is the same and force is the same for both of them. Okay, so I'm going to have, always do that. I'm going to have the 65 kilogram person, okay, over here, right? That's the way I had a person on the left, yeah, 65 kilograms. Okay, and what I know about them is that their initial velocity is 0 meters per second, because it says they're stationary. Okay, and I also know that the time is 0.75 seconds. And that's all I know about the person on the left. So I probably can't do very much with that person, at least at the beginning. Okay. The other person, who has a mass of 80 kilograms, okay, they tell me that their initial velocity is 9.58 meters per second east. Okay, I know the time for them is 0.75 meters per second. Or sorry, not meters per second, seconds. Time is in seconds. Okay. And I know their final velocity, 1.25 meters per second east. Okay, I want to find the final velocity of this person. Okay, so what can I calculate right now with the three givens I have for the 80 kilogram person? I can calculate their acceleration. What can that help me find? F net, yeah. Once I have the acceleration, I can calculate the F net. There's no mention of friction. We've greatly simplified this problem, and there's no friction involved. So whatever the net force is, that's the force acting on the person causing that acceleration. Okay? So I'm going to calculate the acceleration of the person on the left. Or sorry, person on the right. It's BI, or VF minus BI over T, so that's going to be 1.25 minus 9.58, okay, divided by 0.75 seconds. All right, so they have an acceleration of 11.1 meters per second squared west. Okay, because their acceleration is slowing them down. Everybody okay with that? Is that a big acceleration? Bigger than gravity, right? Okay, so that collision would feel worse than if you fell flat on your face. okay? Gravity would give you an acceleration of 9.81 meters per second squared, okay? This would be worse. Now, you've got the cushioning there on the inside, okay, which kind of softens the blow a bit, but like, I had to go to the chiropractor after, okay? Because I got jerked around so bad with the collisions, okay? They're quite, sure, you don't like hit your head and get a concussion, but you still get accelerated pretty well. All right, so now I've got the acceleration of negative 11.1 meters per second squared. Yeah, sorry, I'm gonna say west, because that's what it actually is. West. Okay. Now I'm gonna calculate the F net, because I've got the mass and the acceleration. All right, so F net, mass times the acceleration, times 80. Okay, so 888.53 newtons worth of force is the force that this person exerted. So that is also then the force the other person exerted back. Every action has an equal and opposite reaction. Okay, so that means the force that this person experienced was 888.53 newtons east. Okay, because they were stationary. When that person who was running east hits them, they're going to bounce and go east after that. Is that everyone okay with that? All right. Can I calculate this person's acceleration? Will that help me get their final velocity? Okay. Is their acceleration going to be bigger or smaller than the 80 kilogram person? Bigger. Because they are lighter. Yeah, okay, they have less mass, so they're going to experience a greater acceleration. This is back to the smart car versus semi-truck situation, right? Mass matters. The heavier you are, the less your acceleration is going to be. All right, so we're going to take that 888 and we're going to divide it by 65 kilograms. And yes, okay, we've got, actually, that's positive because I forgot to take the negative off. Right, so their acceleration is 13.67, or actually 13.68 meters per second squared east. Okay, well now I can calculate their final velocity because I know the time is the same for both people. Okay, so A equals VF minus VI over T. Okay, so we'll have A times T plus VI. VI was 0, so don't even have to do that. It's just going to be A times T. All right. So if we could actually see like a video of that, it would look like that person comically flying off when they got hit. Okay, because 10 meters per second is pretty quick. Right, and we only have 2 significant digits here. So the final velocity of that person is 10 meters per second east. Okay. Harder or easier than the 2-box or 3-box questions? I mean, to visualize, like there's a lot less analytical stuff that goes into this. It's like, oh, okay, yeah, the forces are equal and I just have to do some calculating. But I hope you're seeing the pattern here. The ones with less analysis usually have more work, okay? The ones that have less work usually have more analysis, okay? Those 2-box questions, I mean, we had one where we calculated one thing, okay? We calculated the net force and then we were done, okay? So just things to think about, right? Like, you could run into either situation. Okay, I want to have you guys try these 2, and then we're going to go over your labs. Okay. Okay, so we got 2 figure skaters on the ice push off each other. So they're standing right next to each other, and they're just going to do this and just push. Okay, they're not going to try and skate or use their feet at all. Okay, they're just going to push off of each other, and so there'll be the equal and opposite force thing going on. Right, so skater 1 has a mass of 79 kilograms, okay, and accelerates at 2.5 meters per second squared. Right, and we'll just say that that'll be the positive direction. Okay, so we'll say this way is positive, okay, and the other way will be negative. Okay, skater 2 accelerates at negative 3.6 meters per second. We don't know that person's mass, but we know that they're going to accelerate at negative 3.6 meters per second squared. Okay, what can I calculate about the 79 kilogram person? F net. Okay, so F net's m times a, and that'll give us the force that they experienced. So 79 times 2.5. Okay, where else can I use 197.5 newtons to the left? I can use it for the other person, except I'll make it right. Negative, right. Wrong. Whichever. Okay? Yeah. Okay, so I can use that force over here, 197.5, which will easily allow me to calculate the mass of this person. And by simply going 197.5 F net divided by 3.6. Okay, because both of those are negative, okay, in this case. Okay, and that answer makes sense. Okay, they are less massive than the other person, which is why they experience a greater acceleration than the other person. Okay, so 55 kilograms would be the mass of the other skater. Okay, everybody all right with that? Okay. All right, then the two Sherpa question, okay, is just like the other two mass questions, or two, like the logs question we did yesterday, okay, and any of the two box questions that we did. So 2 packs of gear are connected by a rope along, and they're being dragged along the ice field. So here's our 2 packs of gear. Okay, pack A is 90 kilograms, and pack B is 70 kilograms. Okay, and the acceleration of the packs is positive 1.1 meters per second squared. The force of friction acting on pack A is 92 newtons. Okay, packs are pulled by a rope attached to pack A using a force of 7.1 times 10 to the 2 newtons. Okay, what is the force exerted by pack A on pack B? All right. Can I use pack B for anything here? No, I know nothing about pack B other, well, I can calculate its net force. That's it. Okay, it's not going to help me because I don't know how much friction is acting on it, and I have no way to calculate that, right? But I do know lots of the forces acting on the first pack, right? So I'm just going to get rid of the second pack because I really don't need it for anything in this problem. Okay, so I'm just going to make this now the force of pack B on A, and I'm going to add one more force here, the force of friction, because they told us that that was 92 newtons. Okay, so I've got the force of friction, I've got the applied force acting on here. What else can I calculate about this box? I can calculate F net because they told me the acceleration of the system. Okay, so we'll go F net equals m times a, so 90 kilograms times 1.1. Okay, so I can't believe I punched that into the calculator. Need a holiday. 99 newtons. Okay. All right, so our F net is 99 newtons, and that's in a positive direction. So can I calculate now the missing force? Yeah, it's just the sum of all forces calculation then, right? F net is the sum of the force of B on A plus the force of friction plus the applied force. Okay, so we just solve for the one we don't know, right? So the force of B on A will be the net force, 99, minus the applied force, 710, minus the force of friction, negative 92. Okay. And that's going to give us a negative number, as it should. Okay, so the force of the second pack behind or dragging on the first pack is going to be 5.2 times 10 to the 2 newtons backwards. Okay, everybody all right with that? All right. Your unit exam will have one or the other. It'll either have two things running into each other as a Newton's third law question, or it'll have two boxes as a Newton's third law question, or two packs or two logs. Okay, but that type, it's gonna be one or the other. Okay? All right, let's have you bring out your phones, and on your phone have your lab report so that you can have a look over that.